let's get into it. We're going to talk about representation theory. We're going to start with some matrices, and by the end, we're going to have cool pictures like this. The point of this video is to try and motivate why we need something more than linear algebra if we're interested in working with more than one object. So these two matrices here are pretty simple. If you look at what they do to a vector, like this thing just switches the y and z coordinates if we multiply by a, whereas this thing just kind of cycles through those entries. Now you can check that these matrices do not commute with each other, and each matrix is actually diagonalizable. You just can't do it at the same time, and I'm going to explain why. You're going to see some complex numbers in here. This whole series is going to be working over the complex numbers. When I teach my students about diagonalization, I like to draw lots of pictures because I think it really helps explain what's going on. So up here, our first matrix, if you work it out, it has two eigenvalues, 1 and -1. Remember, that was the matrix that just swapped the y and z entries. So if I swap the y and z entries here or here, it actually doesn't change the vector at all. So those vectors are going to have eigenvalue 1. And I shaded this in because there's actually a two-dimensional eigenspace with lambda equals 1. There's also this sneaky guy up here who has eigenvalue -1 because when we switch those entries, it's the same as multiplying that vector by -1. Since we have found a basis for our three-dimensional space consisting of eigenvectors, we can actually diagonalize this matrix. So in that basis, everything is just diagonal, pretty nice. However, when we turn to that second matrix, remember that was the one that permuted, that cycled through things? If you actually look for real eigenvectors, there's only one, just the matrix 1, 1, 1. Of course, if you cycle through, it stays the same, so lambda is going to be equal to 1. But if you allow yourself complex numbers, if you allow yourself to have a cube root of 1, which of course there is in the complex numbers, we call that omega, then this cool vector here, 1 omega omega squared, when we kind of cycle it through, it has the effect of just multiplying by, in this case, omega squared, or in this case, omega. So again, we have a basis of our three-dimensional space that is made up of these eigenvectors, so B can be diagonalized as well, and it would look like that. Now you, of course, have noticed that the bases we chose here are very different. And in fact, it's true no matter how hard you try, there's never going to be a way to simultaneously find a basis that makes both A and B diagonalizable. It's not a coincidence that I've put that right under this fact that they don't commute. In fact, two matrices that are separately diagonalizable will be simultaneously diagonalizable if and only if they commute. Phew, what a mouthful. So maybe that's the best we can do, right? We can't diagonalize both of them. But let's try to step back and think about what an eigenvector is more abstractly. So what is an eigenvector? Well, an eigenvector is something that gets sent to a multiple of itself, and we're going to ignore the case that it gets kind of contracted to 0. And so if we think about the line spanned by that eigenvector, well, that line gets sent to itself. That line might get stretched by a factor of 2 or by a factor of 1/2, but it still goes to itself. So the vector won't be invariant because it might get stretched, but the line will be. And so we call that A invariant because it's invariant under our thing A. And a line, well, a line is just a one-dimensional subspace. And so maybe there's some bigger subspace, maybe 2 or 3 or 4-dimensional, that is actually invariant in this same way. That's what we're going to call it for something to be A invariant. And so if we're doing something simultaneously, we're looking for things that are going to be A invariant and B invariant. And so if you wanted, say, simultaneous diagonalizability, you're going to be looking for one-dimensional subspaces. Those are going to be things spanned by eigenvectors that are going to be fixed by both A and B. And remember, for our matrices, we couldn't do that. There was no way of finding kind of 3 eigenvectors that we could choose in our basis to make those matrices diagonal. Here are our two matrices again, and you may have noticed earlier in the video that the vector 1, 1, 1 is actually an eigenvector for both. So both matrices are going to send that line, this green line, to itself, so that line is invariant. And also, you can check that if you start with a vector whose entries sum to 0, well, if the entries sum to 0, whether you swap 2 of the entries or you permute them, that property is still going to be preserved. So this pink, it's actually a two-dimensional subspace, is actually going to be invariant under both matrices. And so if I make up this notation down here, we might say that these two spaces are A and B invariant. And this is how the first video is going to end, because if we take those two spaces, the green one-dimensional space, and say we pick a basis for that pink space, if we write down these matrices with respect to now the same basis for both of them, look at what we get. We get some sort of block matrices. Now notice that neither of them is diagonal, but the fact that we've split it up actually means that our big vector space C3 actually splits up into 2 smaller ones, a line and a plane, in such a way that when we look at the matrices A and B, They're like just going between like U1 and itself. But this is the main idea of representation theory, is you look at matrices, or more generally you look at like a set of matrices, and you try to see, is there something that's going to be fixed by all of them, and how can we decompose those things? I hope you're having fun with this series. If you could like or comment on this video, it really helps get this out to people who might be interested. Thanks for watching until the end.